This video is for assignment A number 6 on trig integration, and I'm just going to do some examples. First, it's good to recall some trig identities. The main Pythagorean identity, that's sine squared x plus cosine squared x is equal to 1, and tan squared x plus 1 equals secant squared x. And then a variation on the double angle identity is that cosine squared x, or maybe this is called the power reducing formula, and sine squared x is equal to 1 minus cosine 2x. So these are essentially just integration by substitution problems that we're going to look at, but they're just harder than the problems that are on the BC Calculus test. So the first one is the integral from indefinite integral sine cubed x cosine to the 4th x, dx in there. And so we are trying to find a u sub that will make this work. Now, if you just tried, say, u equals sine x, then your du would be cosine x, but your du would have this 4th power in it, and so it wouldn't work out very well. And so you just have to figure out a clever way of kind of making this work, and I think it helps to kind of see it in context. So I'm just going to go ahead and do the problem and then see if we can figure out some strategies to how I knew exactly what to do here. So keep in mind that you can replace sine squared in terms of cosine squareds, and so we're going to take advantage of that here. So if I take this sine squared and the cosine to the 4th x, then I still have an extra sine x that's not accounted for, so I'm going to write it there. And then notice that the sine squared can get replaced with 1 minus cosine squared. And then I've got the cosine to the 4th power, and I've got this extra sine x dx. Well, that ends up being great, because if I let u equal cosine x now, then the du has the sine x in it, and I will be able to solve the integral. I think it's helpful to go ahead and distribute the cosine to the 4th through here, so it is cosine to the 4th x minus cosine to the 6th x times the sine x dx. So now we're ready to do the u substitution, which will be that u is equal to cosine, and du is equal to negative sine x dx, and we can put the negative over there. And so then this will become u to the 4th minus u to the 6th times du with a negative out in front, which means I could make it u to the 6th minus u to the 4th du will be 1/7 u to the 7th minus 1/5 u to the 5th plus c, which will be 1/7 cosine x to the 7th minus 1, sorry about that, 1/5 cosine x to the 5th plus c. Clean that up a tiny bit here, so it can just be cosine to the 7th minus 1/5 cosine to the 5th plus c. It's supposed to be a 5. All right, so that's the first example, and I'm just looking for a way to replace one of the trig terms such that I still have one left over for my du part, but all the rest are in terms of cosine. Now there might have been a way to do this problem by replacing, ending up with an extra cosine here, but it helped that the sine was an odd power so that I could get rid of the squared and have one extra, and then this was kind of neutral in the problem. This cosine could have been any power, but using the odd power to be your du, meaning, and the even power to be your u sub is perhaps a good tip, but you'll have to play around with them and just know that it's just a u substitution. So here's the next example. It is the integral with cosine cubed x over the square root of sine x dx. And I'm going to go ahead and get everything as a power. So this will be sine to the -1/2 x cosine, and here's this odd one. I'm going to go ahead and break that up and see if I can get anything to get a little better with that. So cosine squared times cosine is cosine cubed. It's pretty clear I'm not going to be able to use one of these identities with the sine to the -1/2. So hopefully something will get better with the cosines. So I'm going to leave this sine -1/2 x, and then the cosine squared could be replaced with 1 minus sine squared. And then I still have a cosine x dx, which is fine because that will help with my u substitution. All right, so I'm going to distribute this through here. So I will have a sine -1/2 x, and then -1/2 exponent combined with the -2, or with the +2 exponent, will give me a minus sine to the 3/2 x, and then the cosine x dx. So I think we're ready for the u sub now. And I think hopefully it's clear that if you let u equal sine x, then the du is cosine x. So then this will become the integral of u to the -1/2 minus u to the 3/2 times du. So then the antiderivative of u to the -1/2 is u to the +1/2 times 2 minus u, if I add 1 to this, it'll be 5/2 and 2/5 plus c. So this will be 2 sine to the 1/2 x minus 2/5 sine to the 5/2 x plus c. All right, that's examples 1 and 2, and we're going to do 2 more to kind of get everything here. If we were in class, I might just do 1 more and then have you work on one in class together. Let's do the integral of cosine to the 4th x dx. So this one doesn't have the benefit of having both a sine and a cosine in it, so I think we're going to need the other formula here. That's basically this one. So if you think of this cosine to the 4th x as cosine squared x squared, then I can substitute in this So this will be 1 plus cosine 2x over 2 squared. And then, believe it or not, this is something we can deal with because we can square it, and the denominator will become a 1/4. And then the numerator is just a binomial, so 1 plus 2 cosine 2x plus cosine squared 2x. And then this one, cosine squared 2x, we're going to need to apply this again. So a good way to do that is to break this up into different integrals. So I can have 1/4 of the integral of 1 dx minus 1/4, and then this 2 can come out in the integral of cosine 2x dx. And then I'm going to have plus 1/4, and then I'm going to use this formula again, and it has a 2 in the bottom, so that can be a 1/2 out here. And then the cosine squared 2x just becomes 1 plus cosine 2x dx. Alright, so I'm done with the identities, and I can figure out the rest of this. The antiderivative of 1 is just x, so I have a 1/4 x, and then 2/4 here, and the antiderivative of cosine 2x definitely involves a sine 2x, but the derivative of sine 2x is cosine 2x times 2, so I need a 1/2 there, and then this will become 1/8, and the antiderivative of 1 is x, and the antiderivative of cosine 2x is a sine 2x, and then we just did this, sine 2x, cosine 2x times 2, so I need a 1/2, and then a plus c. Oh, I made a mistake. Shoot. This cosine 2x, cosine squared 2x, becomes the cosine of double that. So this, when I applied the identity that took cosine squared x to this needed to become a 4. Going to change the next line also. So applying this identity, whatever this input value is here, the output, the side over here is double whatever this is. So since this was already 2x, then this becomes 4x when I change it. And so then this is a 4x, and the sine of 4x gives me cosine 4x times 4. So this 1/2 needs to be a 1/4. Sorry about that. And we may as well fix this while we're correcting, since that's hard to read. I'm not changing that, it was just an 8 that didn't come out very nice. Still not very nice. Alright, so cleaning that up a little, we've got 1/4 x minus, those 2's can cancel, so 1/4 sine 2x plus 1/8 x plus 1 over 32 sine 4x plus c. And you could take one more step and combine those, but I think I'll keep the video moving here and move on. It'll end up being 3/8 x plus sine 2x over 4, if you like, and sine 4x over 32. All right, last example. I think maybe we'll just, well,